Let's look now at what happens when waves meet each other and add together. So to start off, just to motivate things and look at a simple example, I've got a couple of animations here. In this case, we have two Gaussian pulses of equal amplitude, and they're propagating towards each other, so they're going to meet and add up and then pass through each other like this. Here they go, they add up and pass through each other. At the moment when they meet, we see we end up with a Gaussian pulse which is twice the amplitude of the individual pulses. In this situation, the pulses are out of phase. This one is negative, this one's positive, and we see when they add up, for an instant, the amplitude drops to 0. So we go up here and we can see the amplitude instantaneously drops to 0. So this first case we would call constructive interference because the waves add up and give you a bigger wave. In this case, we call it destructive interference because the waves destroy each other, and at least in this case, for one instant, we have an amplitude of 0. Mathematically, what we would do would be write down the total wave as a linear superposition of all the individual waves. So here we have wave A1, wave A2. They are solutions to the wave equation, so they act on this argument of the form kx minus omega t. The total wave is given by the sum of these two waves, or if we had more waves, we just keep adding them up. Provided your system is linear, this principle of linear superposition holds. That's what it means to be linear. Something you may ponder for this second example here is at the instant where the wave amplitude drops to 0, where has the energy gone? Here's a little Mathematica demonstration of wave interference. So we have two waves with amplitudes A1 and A2, and if I separate them here, you can see we have one wave which is yellow, another wave which is blue, and the thick green line, is the sum of these two waves. Now they both start with an amplitude of 1 each, and this slider here is the relative phase between the waves. So relative phase of 0, the waves add up constructively, and the resulting wave is twice as large. If I shift the phase until they're out of phase, so the phase is equal to pi, like so, then we have a wave which is cancelled out. So the blue wave cancels out the yellow wave, and the result is 0 everywhere. And as this phase slides through, then we go back to a case of ideal constructive interference. There's a special case here where the sum of the two waves is equal to the initial amplitude of both waves. Might be interesting to calculate what that phase is. If you start off with two waves of equal amplitude, what phase gives you a resultant wave with the same amplitude? And of course, if we imagine these are waves instead of just curves on a graph, then these all animate. So if these are waves that are traveling, they're all traveling at the same speed, then we add up the yellow wave and the blue wave and we get the green wave.